Hi everybody, so we are back again on network theory, right? So today I'm going to talk about electrical resonance, okay? Already we started with AC circuits and we have talked about phasor, right? And now it's time where you have to, solve the PYQ, right? So I have started solving PYQ as well in the back side, okay? So you have to start with instrumentation, then go for electrical engineering, then go for electronics. So that should be your okay. So this session is going to be on electrical resonance, right? Electrical resonance, okay, and it is one of the very important topic for any branch of engineering, right? So hi everybody. Uh, yes. So what is electrical resonance and when we can have the electrical resonance? Okay, so electrical resonance is nothing but a phenomena in electrical circuit, right? Where the applied voltage and the current, source current, you can say, they will be in phase, right? So it is what the very first definition that you should know what is electrical resonance. In fact, we have seen also, right? When your overall circuit becomes the purely resistive circuit, okay, and the reactances are same, okay, whether you talk about capacitive reactance or inductive reactance, right? And your entire circuit becomes same, and the source source voltage and the source current are going to be in the phase, right? So the resonance is just a phenomena, you can say it is a phenomena, okay, in the electrical circuit, phenomenon in the electrical, okay, circuit, right? uh where where the applied where the applied voltage, okay, and the source current are in phase. Okay, so this is first and foremost, definition that you have to keep in mind. What is resonance? Okay, whenever there will be a resonance in the circuit, please keep in mind the voltage and the current, they will be in same phase, right? And the entire circuit will be what? And the entire circuit is going to be purely resistive circuit, okay, purely resistive circuit, okay. So at resonance, the second point that you have to keep in mind is at resonance, okay, at resonance, uh at resonance condition, okay, the circuit we have, you can say circuit we have, okay, as purely resistive, okay, as purely resistive, right? So suppose you have got any impedance, right? So what you can do always is the imaginary part you can make it zero, right? Okay, suppose any circuit is given and there is a resonance condition, okay, present in the circuit, right? So if you're computing you can say the impedance, or if you're computing the admittance, right? So in that case, imaginary part you can make it zero, right? Because entire overall circuit should be purely resistive circuit, right? So the imaginary part should not be present. These 2 points you have to keep in mind, okay. And we have to also find, at resonance condition we will get one frequency, we call it resonance frequency, right? So resonance, the third point that you have to keep in mind, okay. So resonance is what? The resonance is the frequency response, okay. Resonance is the frequency response of electrical circuit, right? Electrical circuit, okay. So all these conditions that you have to keep in mind, that's it, okay, while solving the question. Resonance is the frequency response of the electrical circuit such that okay. So if you want to have the resonance, keep in mind there should be inductor, there should be capacitor, and there should be resistor, okay. Okay, if suppose resistance is not present, only inductor and capacitor are present, right? So there will not be any resonance, right? So to have the resonance, you should have a storing element, okay. You should have Okay, I hope this makes sense to you, right? So for resonance, you have to keep in mind storing elements should be present in the circuit, okay, along with the resistor. So resonance is the frequency of the frequency response of electrical circuit, right? So I should write here the frequency response of electrical circuit such that at resonant frequency, you know, in the exam, in the question, they will ask you what is the resonant frequency. So you have to always keep in mind, we have to find the resonance frequency. Resonant frequency, you can say, at resonance condition, right? So resonance is the frequency response of electrical circuit such that at resonance frequency, okay, omega naught, right? Omega naught, the net reactance, okay, the reactance, okay, net reactance is equal to, okay, or you can say net impedance, not reactance, net impedance is equal to, okay, is equal to resistance only, is equal to resistance only. So this is very important point that you have to remember. Resonance is the frequency response of electrical circuit such that at resonance frequency omega naught, the impedance is equal to 0. What is the meaning of that? Net impedance is equal to resistance, means net reactance should be equal to 0. Net reactance should be equal to 0. Or you can say that in other words, imaginary part of impedance, okay, should be equal to 0 at resonance. This is very important, right? So if you want to find the resonant frequency, so you have to always equate you have to always equate imaginary part of the impedance to 0 so that you can find that frequency, right? So suppose we have got z equal to r plus jx, right? This x is nothing but a net reactance, you can say. If it is an inductive circuit, so there will be xl. If there is a capacitive circuit, you know, capacitive reactance is present, so xc, or both are present, then xl minus xa, depending upon which one is greater, right? So this guy should be equal to 0 at resonance. So this guy should be equal to 0 at resonance. I hope this makes sense. So in any electrical circuit, resonance can occur, okay? In any electrical circuit, okay? In any electrical circuit, the resonance can occur provided we have two similar but opposite uh, nature of energy storage elements should be there, okay? In any electrical circuit, the resonance can occur. That's what I have told you also. That's what I'm now writing, okay? So you have to keep in mind so that your notes will become good, right? See, when resonance can occur in the circuit, okay, so that you should know. So in any electrical circuit, resonance can occur, okay, provided we have, okay, we have two similar but opposite nature of, okay, two similar but opposite nature of energy storage element, okay, like you can say L and C are present. So I think this is clear, okay? So resonance, when resonance will occur, okay, when resonance will occur, guys, resonance will occur provided we have two similar but opposite nature of the energy storage elements are present, like L and C. Okay, if L and C are not present, then you can't have the resonance. Okay, so these points you have to keep in mind. Okay. And if you want to have the resonance in the circuit, so you need to connect good inductor as well as good capacitor. That is also very important. Okay, so you can say to undergo resonance. Okay, to undergo resonance, we need good inductor and good capacitor. Okay, these storing elements should be very good, right? So now the question is, how do we measure this goodness of these storing element? How do we measure the goodness? How do we measure the quality of inductor and the capacitor? Can somebody tell me in the chat box if somebody is live right now, so they can answer me? Okay, because if you want resonance to happen in the electrical circuit, so these electrical elements like L and C, these storing elements, okay, should be present, but they should be of good. Okay, like the quality should be amazing, right? Quality should be good. But how do we measure that quality? How do we measure that the goodness of the inductor and the capacitor? Okay, so there is one factor, we call it quality factor. I think everybody might have heard about quality factor, right? Sometimes we call it figure of merit as well, right? So the goodness, or you can say the goodness, or you can say goodness, or you can say the quality of inductor, okay, inductors and capacitor, okay, is measured in terms of quality factor. Okay, quality factor. This is the reason we study quality factor. We talk about quality factor, right? Okay, because we need good inductor and the good capacitor. So quality factor will describe, okay, about the storing element, okay, storage element, whether they are good or bad, right? So goodness or quality of inductor and the capacitor is measured in terms of quality factor. We denote it by capital Q. And sometimes we call it this Q, sometimes we call it figure of merit. Okay, please remember these points. So I think this is clear. So good fact, okay, measured in terms of quality factor, and the Q is nothing but a, okay. So now we should discuss what is the minimum Q that is required, okay, so that your electrical circuit will undergo resonance, right? So you can say that the minimum quality factor, okay, quality factor. I will define quality factor again. Quality factor, what is quality factor and all. Okay, but you should know this is just a measure, right, of measure of goodness, or you can say measure of quality of good inductor as well as the good capacitor, right? So the minimum quality factor, right? Minimum quality factor we need to undergo, you can say, undergo resonance, okay, is okay, in practical circuit, you can say, in practical circuit, okay, is what? That is 10, right? So minimum it is 10, okay. I hope this makes sense. And maximum as high as like 100, that you can say. The maxima and minima, that you should know, right? So these are the some you can say some idea that you can have, right? Some figure, minimum quality factor which is needed to undergo resonance in practical circuit is nearly 10, and the maximum resonance, you can say okay. So like tuned the filter, okay, for tuned filter kind of application, okay, you need at least 100. So maximum you can have is 101, right? Now let us define what is Q factor, right? Now the question is, what is Q factor? So Q factor is nothing but a ratio that you have to understand. You know, Q factor you can compute by 2 pi times, okay. Q factor is just a ratio of maximum energy stored, okay, maximum energy stored, maximum energy stored per cycle, okay, of supply upon the maximum energy dissipated. So maximum energy stored upon maximum energy dissipated, that is gonna be defined as Q factor, okay. So maximum energy dissipated, okay. Suppose inductor is there, pure inductor is there, okay, and there is no resistance. So in that case there will not be any kind of dissipation, right? So Q factor will be what? You can think about Q factor now, right? So Q factor is nothing but 2 pi times the maximum energy stored, right, in one cycle, you can say, upon maximum energy dissipated, maximum energy dissipated per cycle of supply. So store energy stored upon energy dissipated is going to be called as Q factor, okay. Q factor 2 pi times that you have to write. Okay, so let us talk about some of the Q factors, some standard Q factor that you should know, right? So suppose I talk about some element, the passive elements, and we will also see, we will combine those elements like R and L, R and C, okay, and we can combine them in series and parallel manner, and we will see the Q factor, okay. Please remember these points, right? So Q factor is nothing but what? Maximum energy stored per cycle of the supply upon maximum energy dissipated. Maximum energy stored upon dissipation. So if you see the pure inductor or a pure capacitor, so there will not be any kind of dissipation, right? So you can think about the Q factor, okay. So here I'm going to write the elements, right? So here I'm going to write the element, okay, element, and here I'm going to write the Q factor corresponding to that, okay. So as I told you, whenever RLCs are present, right, and the AC input is given, so you have to always think about it, right? Which one is dominating? XL is greater than XC or XC is... We never take care of this, okay? If suppose somebody is asking what is the input impedance of given circuit, right? We always attack to try to find input impedance or something. We never care about, okay? So you need to focus on that also, okay? So suppose element we have got is, first element is in resistor. The resistance is the first element that we can have. In resistance there is no storing capacity. You know, resistance does not have any storage. Okay, resistance is memoryless device, you can say. Okay, resistance can dissipate only. So the numerator of Q factor is 0, right? So you can say Q factor is gonna be 0 for this. I think anybody can relate. For resistor the Q factor is 0, right? Okay, and if I talk about inductor, if I talk about capacitor, okay, for inductor as well as for capacitor, the Q is going to be infinity. Q is going to be infinity. Why? What is the reason? I think now you can understand, okay. So those who are live right now, they are watching me, right? So they can really understand, okay, why Q factor for inductor is 0, or why Q factor for inductor is infinity, because there is no dissipation in the pure inductor, right? In pure inductor you can't have any sort of, I'm talking about pure ideal inductor, right? Ideal capacitor, okay, pure one. So Q is going to be infinite, okay. And suppose I'm going to combine R and L, right? I'm going to combine R and L, right? So let me write these things in the next slide. So here suppose element, and here suppose Q factor. Okay, so this kind of question also you can expect, right, from the Q factor. They might ask what is the Q factor of the given circuit, right? So you should know these. So suppose series RL is there, right? So this is nothing but series RL. Series RL. Okay, so I'm not gonna prove here how we have got this Q factor, but you should know this Q factor is nothing but omega times L by R. Omega times L by R. Okay. So I think this is clear. Okay, omega times L by R for series RL. Okay, this is nothing but series R. Remark, you can say, remark. Series RL circuit. Okay. Series RL omega L by R. This R will be always in the denominator. Why? Because the Q factor is defined as 2 pi times the maximum energy stored upon maximum energy dissipated. So resistance should be always in the denominator, right? And if you get series RC, okay, series RC, this L by R, is nothing but the constant of, you can say time constant of the circuit, L by R, right? And omega times the time constant of the circuit, right? Okay, so you can say RC. What is RC? What is the Q for RC? Q is going to be 1 by omega RC, right? 1 by omega CR, and this is nothing but series RC. Series RC, okay. Suppose at certain frequency some Q is given, right? Then at certain frequency, what will be that Q? So don't take it like Q is proportional to frequency. Okay, you need to find L by R, and then you can plug that L by R. Okay, because these L by R will be constant, right? And your omega is varying, so you need to find L by R. Suppose one Q factor is given for at certain frequency. Again, they are asking what will be the Q factor at that frequency. You can find L by R, time constant of the circuit, and then you can go ahead. This kind of question has been asked in instrumentation branch. Okay, suppose we talk about R, L, and C. R, L, and C. What is that Q factor for this? Right? For this, Q factor is going to be 1 by R square root of L by C. Okay. Q equal to 1 by R square root of L by C. So this R will always be in the denominator. That you have to keep in mind. Okay, 1 by R square root of L by C. Okay, sometimes in the exam they directly ask question, what will be Q factor, quality factor of this circuit? Okay, so you should know these formulas. 1 by R, you can derive also, right? If you know zeta of the zeta, okay, damping ratio, okay, in control system, I think everybody might have seen. So those things I will discuss also, right? When I will discuss Laplace transform analysis, okay, or steady state analysis. So ये याद रखना. And this is series RLC, right? So from this also you can have questions, some easy question you can have. And suppose there are elements, and this is the Q factor. Now I'm going to talk about parallel combination. So I'm just going to connect, L and R. So for series connection, that was omega L by R. For parallel connection, it will be, okay, it is basically, for parallel connection, you can say just take the reciprocal of that. Okay, for series, it is omega L by R. For parallel, it will be reciprocal of that. You can say that it is R by omega L. I think this is clear. Okay, for parallel, for series, it is omega L by R. For parallel, okay, if R and L are connected in parallel, you take the reciprocal of series Q factor. And here I am going to connect capacitance as well as the resistance. What is that? Again, you take reciprocal omega CR or omega RC, you can say. Okay, omega CR or omega RC. And if you connect all guys in parallel, okay, all guys in parallel. So again, you can take the reciprocal of that, RLC. So you have to only remember for one connection for series, and for parallel connection, you can take the reciprocal of that. So what is that reciprocal? Reciprocal is going to be Q equal to R square root of C by L. R square root of C by L. I think this is clear for all. You can say reciprocal, or we are just taking the duality of that, dual nature of the circuit, right? Dual of that. Okay. Dual of that. How? Let me explain you. See, Q series क्या होता है? Q series, that is 1 by R square root of L by C. Now you see Q parallel, I'm talking about Q parallel. So 1 by R here is what? 1 by R is basically a dimension of, you can say, conductance, right? So what is the dual of conductance? It is going to be resistance, right? So just you can say that it is just a resistance, okay? And what is dual of L? That is C. What is dual of C? That is L. So I think with this also you can do like this, okay? Or just take the ratio of that, okay? And that is enough. So if you know series, you can find for parallel. So let us talk about series, series resonance. Okay, for series resonance, you should have all the elements R, L, and C. Right? R, L, and C. Okay. Both elements should be present for resonance. Okay, that is for sure. You have to keep in mind, right? So now I'll talk about series resonance. Series resonance. So this is nothing but R, L, and we are connecting these. You see all elements. And this entire circuit is being driven by a phasor, you can say, some Vm cos omega t or Vm sin omega t, whatever, R, L, and this is C. You can say that this L is nothing but JXL. This C is nothing but minus JXC. Okay? Depending upon the input frequency, right? They will mention some frequency as well. So omega is basically a frequency that you have to keep in mind, and we are going to change this frequency, okay? So what is the impedance that you can have in this circuit? The impedance you can have in the circuit is J times XL minus XC. This is the impedance that you can have. I need not to explain you how we have got this impedance. You should be able to write R, because after all guys are connected in series, right? So you can add them, right? That is what the thing is. So what I said was, this is the impedance, right? Z equal to R plus J times XL minus XC, and this is the net reactance that we have got, okay? So at resonance, what is going to happen at resonance? At resonance I'm talking about, right? At resonance, what you will do, you can make this imaginary part is equal to 0, okay? Because Z is going to be equal to R, so imaginary part is equal to 0. Imaginary part of G equal to 0, or you can say that net reactance is going to be 0, right? All these things we know. X net is going to be 0, or you can say XL minus XC is going to be 0, or you can say XL equal to XC, okay? In order to find what? In order to find resonant frequency, we are doing all these things, right? So you can say that, okay, this guy will be here. So omega L equal to 1 by omega C, right? So you can put naught here, right? Naught, omega naught L, omega naught C. That omega naught represent resonant frequency, right? So now what you can do, you can just you can write omega naught square equal to 1 by LC. Now you can say that omega naught is 1 by square root of LC. And if I want to write in F naught in hertz, right? This is radian per second, okay? This is nothing but in radian per second. Always keep in mind the units. F naught will be 1 by 2 pi square root of LC. So this is the story everywhere you will get, okay? Right. In fact, in oscillator also, when I will teach in analog circuit, oscillator circuits, right? So there also you need to find some frequency and all. So this is how, you have to equate, you have to find impedance first, then you have to equate the imaginary part should be 0, the net reactance should be equal to 0, and this is how this value, okay? So for series RLC circuit, what is the resonant frequency that you should know? That is 1 by uh, 2 pi square root LC, and L and C are known to you. Okay, and this guy is in hertz. I think this is clear. Okay, so as we have got the impedance is nothing but R plus J times omega L minus 1 by omega C, right? So this is the impedance. Now we can talk about reactance diagram. Okay, we can talk about reactance diagram. Reactance diagram. Okay, we can draw the locus of reactance diagram. So what we can do here is how reactance varies with frequency, right? How reactance varies with frequency, that you know, right? So your XL varies with frequency, it is directly proportional, right? And your can see your capacitive reactance varies according to the 1 by omega, right? So you should know all these things, right? Okay. So we'll draw the phasor diagram as well, and we will try to draw here, right? So you see here, suppose we have got this is nothing but J times X. Okay, this is the reactance that I'm talking about, and this is the omega, okay, frequency. Now, as we know that if I talk about XL, right? So XL directly proportional to omega. Okay, XL is directly proportional to omega, that you can understand. Okay, so this is XL. You go on, and one frequency you will get. That frequency is going to be what? Omega naught. That is the resonant frequency. Okay, at which entire circuit will become purely resistive circuit. Okay, that I think you should know. Okay, that I think you should know. So this is nothing but minus Jx. This is nothing but minus Jx. So let me take some condition in this case. Here only I am gonna take some conditions. So case number 1, before I draw the reactance diagram, the case number 1 is going to be what? At omega equal to omega naught. What? At omega equal to omega naught, your Z becomes resistance. Okay, if you put omega equal to omega naught, right? So this net reactance is gonna be 0. At omega equal to omega naught means what? You are measuring impedance at resonant frequency, means you have made assumption that your circuit has undergone resonance, right? So at omega equal to omega naught, suppose any circuit is given and its operating frequency is given, so you need to find the resonance first, resonant frequency. If both matches, it means entire circuit becomes a resistive circuit. In case of analog, you might have seen I have given you some questions, right? So you guys can always relate whatever concept I discussed, right? So I believe this is fine for all. Yeah. Fine. So let's move ahead. Okay. So at omega equal to omega naught, Z is going to be equal to R. This is very important. So what is the phasor here? The phasor diagram that you can draw here, since current is common, right? So you can say that the current is common here. So your voltage will be in, okay, right? So here you can say phi is going to be 0 always, and the power factor is going to be, you can say, unity power factor that you will get at resonance. This is at resonance, right? At resonance. But you have to compare the frequency with the resonance frequency, whether it is greater or lesser, right? The frequency can be less than resonant, frequency can be greater than resonant. Okay, so depending upon that, leading, lagging, you might get. Okay, so please remember these points. The second case that you can have is your omega can be less than omega naught, right? You see here, I'm talking about here. If you are here, right, like your operating frequency is less than this omega naught. Okay, if omega is less than this omega naught, what will happen? This will be greater, right? Your capacitive reactance will be greater. Okay, if your omega is less than omega naught, since it is 1 by omega, right, so it will be greater, not omega L will be greater, right? So you have to remember, if your frequency is less than the resonant frequency, right, so your overall Z will be equal to R minus Jx. Please remember this point. Your overall Z will be R minus Zx. If your frequency is less than omega naught, Okay, so omega naught you can say is one of the point at which the resonance will occur. Less than omega naught, the nature of the nature of the impedance will be, you can say, complex only, but it will be having capacitive reactance, right? Okay, please remember these things. Okay, in this case, if I try to draw the phasor diagram, so common is like, in case of capacitance, what happens? You know, in case of capacitance, current leads. Okay, the board. Okay, current leads always. Okay, so current is going to be here, and the voltage will be here. So this phi is going to be what? This phi will be negative in this case, right? Because this V is lagging, you can. And the third which you can have is the third one, right? Okay, so third one is going to be what? Third one is going to be, if omega is greater than omega naught, omega is greater than omega naught, Z is equal to R plus JX. Okay, so your overall impedance is going to be R plus JX. Here capacitive reactance will not be there. Here it will be you can say inductive reactance will dominate. Okay, if your operating frequency is larger than you can say resonant frequency, these are important point that, and question has been asked, right? Question has been asked in electronics paper, question has been asked in different papers that I have explored already. So after attending the session, please take a look at P/Q. I will share also the P/Q. So here you can say that the current is I and your voltage is leading in this case. Here phi is going to be positive, right? So now we can draw everything. We can draw. So this is below omega naught, the capacitive situation will be there. Here it will be capacitive. If I talk about if omega is less than omega naught, capacitive power factor will be what? The leading power factor you can have, leading power factor. So you can also say that if operating frequency is less than omega naught, the leading power factor, what is the reason behind that? Why leading? Leading because of capacitive, okay, reactance. If your operating frequency is larger than omega naught, so you can have lagging one, right? Lagging power factor. Okay, so if you go to the left of this line, you can say here it will be inductive, and here you can expect that lagging PF. Okay, I think this is clear, and this will be like this. Lagging PF will be there. This is the curve that you can have. Okay, less than that, okay, and greater than that. So I think this is clear, and this will be you can say this is nothing but a capacitive reactance, and this is nothing but, you can say, inductive reactance. Okay, we have drawn and we can subtract them, so you get this kind of situation. Okay, so I think this is clear for all, and this is very important. And you can also draw I versus omega. I versus omega is also important. Current versus omega plot is also important in case of series RLC. If you remember, you can infer many things. So I versus omega. So at one point where omega will be equal to omega naught, that is called as resonance condition, right? Resonance condition. So you know that at resonance, the current is going to be maximum current in case of series. At resonance, the current will be maximum current in case of series resonance, okay, where net reactance is going to be 0, entire circuit will become purely resistive circuit. So at that point of time, you can have the current which is maximum current, that you can have, right, like this, the maximum current. If there is a maximum current, so you can say that the resistance is going to be low resistance. low resistance, okay, low resistance. And if situation will come, right, okay, you can have less current also, right? If current is less, suppose this kind of situation you get, current is less, means this graph is for high R, this graph is for high R, okay. So if the resistance is going to be high, so your current is going to be less only, right? Please remember this. And if I draw impedance versus omega, impedance versus omega, so at omega naught, okay, at omega, yes. So at omega naught, since the current is what? Since the current is low, sorry, high, right? So what can be the impedance value? The impedance value can be here. Okay, if you try to draw Z versus omega naught, impedance value will be minimum here. Impedance value will be minimum. Not like that. Impedance value minimum, and that minimum value will be Z equal to R. Z equal to R at resonance. Okay, and if you are less below omega naught, if you are below omega naught, the nature of the like capacitive reactance will dominate here. Okay, capacitive. And if you go this side, like omega is greater than omega naught, inductive. Okay, so this kind of situation that you have to remember. So this is a graph for Z versus omega. You can also talk about admittance versus omega. Admittance versus omega means admittance will be maximum in case of like this at omega naught. Okay, just reciprocal of impedance, it is called the, okay. And you can also talk about phase versus omega. So these are the plots, they will give you some basic idea, okay, while solving the question. Okay, what you can do here is that you can say that phase is going to be like this. So the maximum phase that you can have from the series is plus 90 to minus 90, and this is the omega naught. Okay, so your phase will vary like this. Okay. I hope this makes sense to you, right? So this is the phase plot that you can have. And if I talk about Q factor at resonance, what is going to be Q factor at resonance? Q factor at resonance. It is also important because we know that Q factor of the series RLC circuit is what? 1 by R square root of L by C. But what is the Q factor at resonance? So Q factor is basically what? Omega naught L by R, right? Omega naught L by R, right? It is going to be equal to 1 by omega naught RC, right? But we know that omega naught is nothing but 1 by square root of LC. So if you put here, so it will give you 1 by R square root of LC. Okay, you can put all these values. At omega naught, you put the value, right? You will be getting this. See, your Q factor is nothing but what? Q factor of the circuit when it is at resonance is going to be omega naught L by R. Okay, so you can put in place of omega naught, you will get 1 by R square root of LC only. So I think this is clear for all, and so complete phasor diagram, if I try to draw for for series RLC, right? Let me draw the complete phasor diagram for this. So these are the things that you have to always discuss, right? So complete phasor diagram, okay, for series RLC, right? For series RLC, you know that it will be like current will be in the same phase, okay, because if you are talking at resonance, right? So this is R, this is L, this is C, and this guy is being driven by some source, right? And this is a current I, this is R, this is L, this is C. Okay, you can talk about some voltage here. So voltage VR, VL, and the voltage across this is VC, right? And this is the total voltage that you can have, right? So the reference is going to be current, and this is VR, this is VR. And what you can do here is you can say that this will be equal to, you know, VC VL, right? Here VL and this is VC. They will be same. They will be same. Okay. At resonance, these voltages are going to be same. So if these voltages are same, then you can say that your source voltage will be equal to the voltage across the resistance. If someone is going to ask you what is the voltage that will appear across resistance when your circuit has undergone resonance, that so you can directly say that, yeah, that source voltage itself is the what is going to appear across the resistor. Okay, so these points you have to remember. So during series resonance, okay, so I'm just going to write something, some conclusion you can, okay, conclusion, okay, for solving questions. Okay, these conclusion basically will help you to solve questions, right? So please remember. So the number one conclusion is what? During series resonance, okay, during series resonance, if the circuit is series, right, all the elements are connected in series, we call it series resonance. In during series resonance, the net impedance is minimum, not maximum. Remember, it is minimum because the current will be maximum, right? So series impedance, the impedance is minimum. Okay, hence it is called as acceptor circuit, right? This circuit is known as acceptor circuit. Please remember, acceptor circuit we call it. Okay, and since the entire source voltage, entire supply voltage will appear across the resistor. Okay, understood? So you can say that this kind of circuit is also known as voltage amplification circuit. Okay, so you need to keep this in mind, since entire supply voltage appear across resistor. Okay, series resonant circuit is called as voltage amplification circuit, right? Please remember, voltage amplification. So your voltage will be amplified. Okay, remember this. So what we can do here is, now we can compute okay, in series RLC circuit only we can compute I. So I is going to be your VS by Z, right? So VS is nothing but I'm just talking about VS magnitude here. So that will be square root of you know, R square plus you know, omega L, right? Omega L minus 1 by omega C whole square. So at, you can say that, but I'm talking about magnitude of current, right? Magnitude of current, the magnitude of voltage, right? Magnitude of current, magnitude of voltage. So at omega equal to omega naught, okay, at omega equal to omega naught, what you can have here is your VR will be equal to VS. Your VR is going to be equal to VS. Please remember these things, right? Or you can, in other words, you can say that at omega equal to omega naught, XL will be equal to XC, right? So this will be equal to like Z will be equal to okay, so you can say that I naught max is going to be Vs by R, where R is going to be minimum. If current is maximum, R will be minimum, right? You can say that your VR is going to be I times R, right? You can say Vs by R times R is Vs. Okay. This will be the voltage across the resistor. Okay. Now the question is, what will be voltage across the capacitor? What will be voltage across the inductor, right? So these kind of questions they might ask. Okay, please remember this. Okay, given series circuit, okay, and your circuit is at resonance, they will ask you what will be the voltage across capacitor, what will be voltage across. So since series resonance circuit is known as voltage amplification circuit, right? So certainly your voltage will be amplified by the quality factor. We'll see that. Okay, so what will be voltage VL? Right? VL is written as what? Current times JXL. Current times JXL, right? So you can write this as, what is I? I is nothing but Vs by R. Right? At resonance, I will be Vs by R, and your XL is nothing but omega L, which is omega naught L. Right? So you can write this as J Vs into omega naught L by R. Omega naught L by R. Okay, so I think this is clear for all, right? What is this omega naught L by R? Okay, what is this omega naught L by R? That is quality factor, right? So please remember these points. Your Vs, so your voltage across the inductor, the voltage across inductor will be J times, okay, J times Q Vs, J times Q Vs. It looks little weird, but yeah, you can see I have proven also. So please remember, I have derived. So when there is an input voltage and they are asking you to compute what is the voltage across inductor, okay, and your circuit is in resonance, so that voltage across inductor is going to be, if they are asking magnitude, it will be Q times Vs, right? It will be Q times Vs, or you can say that it is going to be Q Vs angle 90, angle 90. So I think this is clear for all, right? So let me talk about voltage across the capacitor. That is also important. So Vc is going to be equal to I times minus JXC, which is minus J times I X. I is nothing but what? What is the current which is flowing through the circuit at resonance? That is Vs by R. It is going to be Xc is nothing but 1 by omega C, right? So you can see here, this Vc is going to be minus J times Vs by omega Rc, right? So what is omega Rc? Vc is going to be minus J times Vsq, right? Okay, Q is going to be what? 1 by omega naught Rc, that you know, right? Omega naught you should put, right? At resonance, you should put omega naught so that you can differentiate with the frequency, okay? Omega naught is the resonant frequency that we call it. So here, if I say that, what is Vc? That is Q times Vs, Q times Vs. And the voltage across, the magnitude of voltage across, inductor as well as the capacitor at resonance should be same. So you don't have to wonder. Q times Vs, Q times Vs. If they are asking magnitude of the voltage, so you should say simply Q times Vs. If they are asking along with the phase and all, so you say here it will be phase minus 90 degree, okay, and this will be in volt. So series RLC circuit is known as voltage amplification circuit. So whatever source voltage is there at resonance, voltage across inductor as well as the capacitor will be appearing Q times the source voltage, Q times the Vs, Q times Vs, and Q is nothing but the as you know, right? And how to compute this Q, okay, that I have shown you, right? So please remember this. So this is going to be okay, for series resonance, Q is going to be 1 by R, the square root of L by C, and Vs will be given, you just multiply with Q can answer the question. So please look at the PYQs and you will get many questions based on this. And without derivation, you can solve the question, okay, in one line. Only provided you should know the formula for Q, for series circuit, and simple. And you can verify also. You can verify. So as you have got total voltage is Vs, the voltage across the resistor is Vs plus, Q times Vs angle 90, Q times Vs angle minus 90, right? So I think you can say that this and this get cancelled, this and this will get cancelled, right? So everything is okay. You can cancel or just you say this Vs is equal to Vs only, right? This will be satisfied. That is what the main thing is, right? Okay, so I think this is clear for all, right? So next, this is the session where I have discussed this concept, okay? In the next session, I'm going to talk about parallel resonance as well as I will talk about bandwidth. Okay? So we will discuss bandwidth, okay? Bandwidth is very important. Bandwidth is nothing but a range of frequency for which, we will discuss. That is just a range of frequency, okay? Maximum minus minimum, maximum frequency minus minimum frequency. We'll talk about 3 dB frequency, right? Calculations and all, right? So we'll meet in the next session. This is enough, I guess, yeah. So I hope you might have learned something new and थोड़ा सा तरीका आपको पता चल गया है. So you guys can solve PYQ, right? So my next session will be on, you can say bandwidth. And I'll conclude the session by discussing parallel resonance. Parallel resonance, okay? So the next session will be parallel resonance. Okay, or we call it anti-resonance. And whatever we have discussed, and also we'll discuss about practical parallel resonance circuit, or sometimes we call it, practical parallel resonance circuit, or we call it tank circuit. Tank circuit. So this kind of circuit, parallel resonance means we'll see this kind of a circuit, simple. And one source will be driving entire circuit here, and the tank circuit will be of this kind, right? So, and this is very popular. One resistor, inductor, and one parallel capacitance is connected, right? So, in fact, many questions has been asked, okay, from tank circuit. So this is nothing but a tank circuit, okay? Yes. So if you remember this circuit, so you will find many questions has been asked in the gate examination, right? So this is nothing but a tank circuit, okay, where R and L are connected in series. Okay, so you can get the by 1 from here, you can get the by 2 from here. By is nothing but admittance. What is admittance? Admittance is nothing but the reciprocal of impedance, right? So these two circuits are there, those things we have discussed. So the electrical resonance will be part 2 I'm going to bring again. So I hope you might have enjoyed. So now your sequence of practices will be start with the IN PYQ, okay, then go for electrical engineering PYQ, then go for ECE PYQ. I'm talking about gate 1. And more practice if you want, then you can follow ESE PYQ. So I think this will be enough only, right? You don't have to waste much time on this, right? Because there are other subjects. And why I'm saying to practice, because if you know the concept, you need to practice, so that and write test series, write test series, right? Test series just to evaluate yourself, okay, where you are making mistake, how much time you're taking to solve the question. Thank you. We'll meet in next